Hello everyone. Here is the review for the before we're going to take the test correction, right? So you probably want to go through that first before you come to take those make those corrections. All right. So the first thing we want to address is domain and range, given a graph of a rational function. Remember, the domain is the set of all possible input value, all your possible x value, but not just any x number, right? It would be all the possible input that would actually result in an output value, right? Some of the real numbers are not going to have an output for the function depending on the function rule. So that's what the domain is. Therefore, x values where the function is discontinuous, that means not defined, have to be excluded from the domain, and that is, we exclude all x values of vertical asymptotes and holes. Alright, so when we're looking at the first graph we have here, first we need to determine where are those vertical asymptotes and holes, if any, right? So when I'm looking at the graph of f of x here, there is definitely a vertical asymptote, and that will be at 2 here, right? So we're going to say VA at x equals 2. There is a horizontal asymptote at y. Remember, those are y values, right? It's an invisible horizontal line that the graph is approaching as it approaches infinities. So y equals -1. Okay, so there is no hole in my graph here, so I don't have to worry about a hole. So my domain, I have to exclude all x values that are vertical asymptote and holes. Well, we don't have any hole. We definitely have a VA at 2. Therefore, the domain here, x, cannot be positive 2. That means it can be anything else, right? But not 2. Another way of writing that, you could also use the very formal notation of negative infinity all the way to 2, jump over 2, and then all the way to positive infinity, right? But just saying x cannot be 2 would be good enough for us here. Okay, range. The range is a set of all possible output values. Well, notice how here, this horizontal asymptote, the graph never touches it, right? The graph never crosses it anywhere. Therefore, we're going to have to exclude that y value. And this y value is a -1, right? That's what we said here. So the range will be all the y's this time, cannot, all of them except -1, okay? And there again, you could use a very formal notation saying negative infinity all the way to -1, jump over it, and then start from the other side of it to infinity, right? But just saying y cannot be -1 is good enough. All right. The second graph, let's look at it. So again, domain, we exclude all the vertical asymptotes and holes. So there is obviously a vertical asymptote here at 1, 2, 3, 4. That's -4. So we have a VA at x equals -4. And then here, notice we also have a hole in this graph, right? And this hole will be at -2. So we also have a hole at, and it's at -2, 1. Now, when I'm excluding for the domain, I'm only excluding the x value, right? Because remember, the domain will be all your x values. So I'm only going to exclude -4 and -2 for the domain here. So x cannot be -4, nor can it be -2. And I'm going to leave it here at this notation. For the range now, I'm checking, and well, we already know that there is a y value for the whole at 1. Therefore, we cannot include that in our range, right? And then also we have a horizontal asymptote here at y equals 2. So there is a horizontal asymptote at y equals 2. And notice how the graph never intersects that horizontal asymptote. So the range, we have y cannot be the y value of the whole and the horizontal asymptote. Okay, that's for domain and range. Now let's go to factoring. To do those rational functions, we're going to have to be able to factor, and there are a few things we need to clean up that I noticed when you took the test. So when I'm looking at that, I'm looking for a greatest common factor. Well, both of those terms obviously have a factor of 3, and both of them have at least an x squared. So I'm going to factor out a 3 and an x squared. Now, when you factor out a 3 here on an x squared, 3 is gone, x cubed divided by x squared is x, so we just have an x here. Too many of you would leave that there and stop and say that's the answer. Well, no, not really, because what happened to this one? We had a second term there. When you take that second term and you divide by 3x squared, well, the 3 cancel. X squared over x squared, that also goes to 1, but it doesn't go to 0, so we need something. It goes to 1, right? So we need that 1 there. Anything divided by itself is 1, so we need to show that. Okay, so that's how we would factor that. On this one, you will look here and you will say, okay, well, there is a negative in front of my leading term, so I don't want that. And then we have obviously at least an x, a factor of x in both of those terms, so we're going to factor out a negative and an x. So negative x cubed divided by negative x will be x squared, and the 4x divided by negative x becomes negative 4, okay? And then here we want almost to say, well, we can't factor anything out, but yes, we can, right? We don't want that negative here in front of the x term. That's my leading term in my denominator. So I'm going to factor out that negative. So I'm taking out a negative. And when I factor out a negative, this 3 used to be positive. It's now going to be a negative 3. And that negative x used to be negative. Now it's becoming positive. So I put my x first and then my minus 3. And then if you notice, we have a factor of negative 1 and negative 1, so those will cancel each other out, and we're left with x, and then x. Oh, and by the way, I'm not done factoring here, right? Because now, notice how we have a difference of perfect square, so we're going to factor that one more time, and that will be x plus 2, x minus 2. Every time you have to factor, you have to go all the way as far as you can. Here we're all done, the negative has been cancelled, so we don't need the parentheses, but if you want to put them, you're welcome to put them. Alright, we're done with this one, right? Here we're looking and we're noticing that we have at least a factor of x everywhere, right? X cubed has at least 1x, 1 and 1, right? So we're going to factor out that 1x everywhere. So this here will become 2x squared. Negative 9x squared divided by 9 is negative 9x, and negative 5x divided by x is negative 5. Alright, now we have to ask ourselves, can we factor this any further? And yes, we can, right? So the x, don't forget the x we factored out first. And then what will we have? Well, there are several ways of doing that, right? But the way I like to think about is, what can I multiply to give me 2x squared? Whatever it is, it's going to go here and here. Right? So to get a 2x squared, I need a 2x and an x, right? Multiply those two, you'll get back to your 2x squared. Then I like to look here and I'd like to say, okay, whatever goes here and here has to multiply to give me a negative 5, yes? Now here we have options, right? To get a negative 5, I'm either going to multiply negative 5 times 1, or I'm going to multiply positive 5 times negative 1, right? Those are my options. And then is my negative or my positive 5 coming here or here? So I'm not sure yet, so I'm just going to try. So that's called trial and error. Let's do it in pencil, so you see we're doing trial and error. So I'm going to say, okay, negative 5 and 1. So if I put negative 5 here and a 1 here, when I do my outer and inner multiplication, I need to get back to negative 9x, right? So do it. 2x times 1 will be 2x. Negative 5 times x will be negative 5x. Is there any way, by adding or subtracting those, that I will get a negative 9x here? And that answer will be no, that's not possible, right? So we know that's not a good option. So this time, I'm switching them around, and I'm going to say, let's put the 1 here and the -5 here, because in my mind I keep thinking, okay, I need somehow a -9, and when I'm going to do my outer, I multiply that -5 by a 2, that will give me a -10, right? Okay, so 2 times -5 is -10x, and then 1 times x is just 1x, and when I add those two, I get -9x, which is what I wanted, right? So that's my winner combination. So I'm going to say, okay, I want a +1 here and a -5 here, and that will be your completely factored form, right? This whole thing now is the factored form. Okay. By the way, for this, to factor that, some of you do the grouping method, and there is nothing wrong with it. Please, if you're comfortable with the grouping method, just keep doing it. What I'm doing is just a shortcut. Not a trick, a shortcut. Okay, horizontal asymptote. We only have 3 case scenarios, right? The first case scenario is when the degrees are equal in the numerator and in the denominator. When the degrees are equal, and in this case they are, right? My numerator is a quadratic, denominator is a quadratic as well, so degrees are equal. Then we would know that the horizontal asymptote will be at y equals a over b, where a and b are the leading coefficients of the numerator and the denominator respectively, right? So the leading coefficient of the numerator here will be a -1, and the leading coefficient of the denominator here will be a 3. So -1 over 3 will be my horizontal asymptote, and if you write that, you're going to lose points, because a horizontal asymptote is a horizontal line, therefore I need an equation of a line, y equals, right? Don't forget that. Okay. Look at this one, and here I kind of just mix them all up, because you need to be paying attention, right? The leading term does not mean that it is going to be in the first place if your polynomial in the numerator is not written in standard form. So you have to really pay attention. The leading term in the numerator will be this one, and the denominator is written in standard form, so the leading term is this one. Okay, compare the degrees. That's a cubic, that's a cubic. They are the same, therefore we want a over b, a being the leading coefficient of the leading term, so not 5 but -7, and then leading coefficient of denominator will be 21. So here the horizontal asymptote will be at y equals, don't forget the y equal, -7 over 21, but we're going to simplify this fraction, right? And that will be a -1 over 3. Okay. Now, second case scenario. So the first one was when the degrees were equal. Second case scenario is when the degree in the denominator is greater than the degree in the numerator. So the bottom polynomial has a higher degree than the top polynomial. So this one is linear, this one is quadratic. Denominator polynomial is definitely greater degree than numerator polynomial. When that's the case, well, it's always just going to be y equals 0, it being the horizontal asymptote. Your horizontal asymptote will always be y equals 0. So when you see that, well, that's just going to be y equals 0. Oh, I forgot something up here. I'm going to go back in a second. We need to write that as a limit. Well, the horizontal asymptote are your n behaviors as x approaches your positive or negative infinity. So knowing that, the limit statement will just be the limit as x approaches. And in this case, I could put them together and say positive or negative infinity. Use the name of your function, don't make something up, right? Of p of x equals 0. And we put an equal here because this is a finite value. It's a number, not just a direction like an infinity, right? Okay. Horizontal asymptote here. So again, we're comparing degree. The numerator is a quadratic. The denominator is a quartic. Therefore, obviously, higher degree in the denominator. Horizontal asymptote will be y equals 0. And therefore, the limit here, instead of writing them together, which I could, I'm going to split them because some of you will have them rather separated. So let's just do that. So we're going to go positive infinity, meaning to the right of, don't make up a name, use the name of the function given, and that will be equal to 0. And then again, the other side, as x goes to negative infinity of that same function, will be equal to 0. But I could have written that in one single limit. Shift back up here for a second because I forgot to write the limit statement for this horizontal asymptote. Again, the horizontal asymptote is the same on the left and on the right, so I'm going to use one single limit statement, and I'm going to say the limit as x approaches positive or negative infinity of my f of x function is going to be equal to negative 1/3. And here, the limit as x approaches positive or negative infinity of my function g of x is equal to negative 1/3. Oh, see, that was not done purposely, that we end up with the same horizontal asymptote. It just happened so here. I didn't even pay attention to that. Okay, third case scenario. The degree in the numerator is greater than the degree in the denominator. Doesn't matter by how much greater to decide if there is a horizontal asymptote or not. We just need to know that the numerator has a greater degree than the denominator. Then there is no horizontal asymptote. Now we might have another one, like a slanted or a parabolic, right? But we don't have a horizontal. So here I just put it down. Compare the degree. Top is cubic, bottom is quadratic. Cubic is obviously greater than quadratic as a degree, therefore there is no horizontal asymptote. So we can't make one up, right? None. Now, if for the oblique asymptotes, if the degree is just one more than the degree in the denominator, then that's when we have a slant asymptote, also called oblique asymptote. And because those are linear asymptotes, we write them in that format. So when you're asked to write a linear, slanted or oblique asymptote, you better have y equal, because it's an equation of a line, right? And then an mx plus b. Okay, now b sometimes can be 0, right? But we need mx, and if b is not 0, we need that b as well. Okay, we need to do long division for those, but sometimes we can go by with synthetic division when we have a nice linear denominator. But in this case, I made one where we have a long division to do to review long division as well. So let's do that. So the first thing you need to notice is I have a cubic term, a quadratic term. I do not have a linear term, so I need to add a 0 placeholder. So I'm going to have x cubed plus 2x squared. I am missing the linear term, so I'm adding a 0 placeholder for the x, and then we had a plus 1. And then we're going to do our division, and we divide that by the denominator, which is x squared plus x, and then minus 1. Okay, so we're going to, I need a little thinking bubble here, so I just think I'm going to put my thinking bubble up here. Hopefully that'll be enough. And I want the first here over the first here, right? So x cubed divided by x squared. Simplify that, that gives me an x. So that means I need an x up here. So I'm going to put it over the linear term. And now I multiply this trinomial by x, right? So x times x squared is x cubed. X times x is x squared. X times negative 1 is negative x. Now remember, what we cannot forget here is the subtraction, right? We're subtracting, meaning that becomes a minus, that becomes a minus, that becomes a plus, right? So x cubed minus x cubed goes away to 0. 2x squared minus x squared becomes just an x squared, right? Just one x squared. And then 0 minus minus, that becomes a plus. So 0 plus x will just become x. So plus x. And then bring your next one down, which is the 1. And now, again, we go in our thinking bubble because we still have x squared and x squared. Those are still same degree. So we keep going, and that simplifies to 1. So up here, we're going to have a plus 1. And now we multiply this trinomial by 1, right? So all of that multiplied by 1 will just be x squared plus x minus 1. And remember, we have to subtract, meaning that becomes a minus x squared, so that goes to 0. Here I have a positive x minus x that goes to 0 as well. And then here I have a 1 minus minus becomes plus, so that becomes a 2 here. Okay, the slant asymptote is going to be, if you write down x plus 1 like that, you're not going to get credit for that. This is an algebraic expression. This is not the equation of a line, and a slant asymptote is an invisible line that my graph is following as the x's go to infinity, right? So I need actually to have an equation of a line. Remember to put that y equal. It might seem trivial to you, but it's really not trivial. Mathematically, we need to have proper language, just like you would have to do proper language when you write an essay, right? Proper grammar and vocabulary. That's what we're talking about here for the math language. Now let's write that as a limit. Well, now that's tricky, right? Because we know we're going to go to an infinity, because a slant asymptote, let me use that here, a slant asymptote is going to take my graph, no matter where it is, my graph. So let's imagine I have a vertical asymptote here, and this will be my graph here, and maybe here, right? Well, if that's the case, if that's my slant asymptote here, it's going to take my graph, right? My curve is going to follow this asymptote. So where are those y values going? To negative infinity. Where are those going? Those will be going up to positive infinity, right? But if my slant asymptote will have a negative slope, let's just make one up here, a vertical one, then let's look at this branch, and now that side here will take my curve to a negative infinity, and this one will take it to a positive. So those will be reversed, right? So what's the key here? The key will be the slope of slanted asymptote. A positive slope, take your x going to infinity, takes the y to infinity. The x going to negative infinity takes the y to negative infinity, and a negative slope is vice versa, right? Okay, so let me erase that. And let's put that down here. So what we're looking at here, we have an equation of an asymptote, and I'm going to do a little sketch here. This equation for that asymptote has a y-intercept of 1, and then it has a slope of up 1 over 1. So the equation, this asymptote will go like that. So when I'm writing my limit, the limit as x goes to positive infinity, now I cannot do plus or minus here, right? Because those are two different directions. So the limit as x goes to positive infinity, don't forget your function name of f of x. Well, where is it going? So as I'm going to positive infinity for my x's, where are my y value going? They're also going to infinity. So this will take my function to a positive infinity. And then I'm going to write it up here because I'm running out of room. The limit as x goes to negative infinity of my function f of x. Where is my asymptote taking my function as I'm going toward negative infinity on my end behavior to the left? Well, my asymptote is taking my function values down, down, down to negative infinity. So that will go to negative infinity. Okay? All right, that was all on asymptotes. So we did this one, we did this one. We're almost done, I think. Well, not quite, but almost. Here, we're just going to put it all together, right? So I'm giving you a rational function, and I'm asking you to find some characteristics of that rational function. So the first thing we need to do, sorry about that, I hope that didn't mess up everything. The first thing we need to do, and it sure did,